Go. This video is going to cover what we've seen with reaction rates in chemical equilibrium. I apologize that it's taken me a little while to get this video up. I was having a lot of storage issues with my computer. Hopefully now I will be able to process this video and the sound file that I'm currently making. So, for this particular presentation, you need to be aware of a couple of terms that I'll use a lot. Reaction rate is the change in the amount of any reactant versus the product over time. So as reactant turns into product, you're going to use that to determine a reaction rate. Equilibrium is when you have a reaction that is in balance. So you will have reactants that will turn into products. You do also have products that decompose into reactants. We'll get in a lot more into reversible reactions very soon. A good way of analyzing or determining equilibrium is, or conceptualizing equilibrium, I guess is the better word, is if we have water that's condensed in a bottle. What's happening is when this bottle's open, water can freely evaporate out. When you seal it, water will still evaporate, but eventually get to a point where there is so much concentration of water that it will start to condense on the sides. And we reach an equilibrium point when the amount of evaporation equals the amount of condensation, and the amount of water vapor in the bottle remains constant. And as we are all familiar with these sorts of situations. So the reaction is continuing to go. We are still having water evaporate. However, for every molecule of water that evaporates, I have a water of molecule that might condense. And there is my reaction in this case. Now, we get to a point where this forward reaction of liquid water to gas is equal to this gas to water. And each of those things is possible when we get to equilibrium. We'll talk about as that significance as it relates to reversible reactions very soon. Now here's another example, actually many other examples. Just like we had H2O as a liquid going to H2O as a gas, and H2O as a gas able to go back to a liquid, we have the same possibilities here. We can take nitrogen and hydrogen, turn them into ammonia. However, ammonia can also decompose to form nitrogen and hydrogen. This is the Haber process. This is the process I keep continually stressing to students. This is one that's happening right now in our atmosphere. Lots of carbon dioxide gas, which part of it is human produced, is dissolving in the water of the ocean. And then we make carbonic acid. These actually hydrogen ions pop off. They pop onto other carbonates, overall decreasing the amount of carbonate in the oceans, which is usually what organisms need to build the calcium carbonate shells that they have. I'll talk a little bit more about that later. We also had a video on that, which I was hoping you would understand. So one of these hydrogens pops off, becomes a hydrogen ion, which pops onto another carbonate that's floating around. Then we have two hydrogen carbonates, and those are not as accessible to aquatic life as the carbonate ion, the 2- charge floating around. Sulfur dioxide and oxygen can make sulfur trioxide. This also is an exothermic reaction. It does produce heat. And then we also have the possibility of what we see here. If I have a container with dinitrogen tetroxide, which is a colorless gas, it could produce, and I better fix this, it could produce nitrogen dioxide, which is also a gas. Just wanted to make sure that I don't forget to put the state of matter on here. So smog is nitrogen dioxide, and dinitrogen tetroxide is a colorless gas. So if we had a container that originally was filled with dinitrogen tetroxide, we would see over time an increase in nitrogen dioxide over time, until finally the concentrations of each are equal, so that the amount of dinitrogen tetroxide decomposing into 2 moles or 2 molecules of nitrogen dioxide is the same as the molecules of nitrogen dioxide that are combining to form dinitrogen tetroxide. Reaction rates can be expressed as a function of a constant. Again, this is very much like college level physical chemistry that you don't necessarily need to worry about at this moment. If you go on to become a chemistry major, again, there's plenty of careers in that, and a lot of your focus will be maximizing reactions. However, and understanding orders of reactions, just as a basic introduction, you would need to know that a first order reaction is dependent on the concentration of only one reactant. So if I increase my concentration of dinitrogen tetroxide, I'm also going to increase the reaction rate of dinitrogen tetroxide becoming nitrogen dioxide. This also, when we talk about Le Chatelier's principle later on, will also be relevant. So over time, the concentration of A would change, and this would be a constant rate of reaction. Anytime you see brackets from now on, that is a reference to concentration. This would be the final concentration of a compound A or an element A minus the initial concentration, and then that would be over the final time and the initial time. You will not need to calculate these K values. You will need to calculate other K values, but not this particular one. So just to understand that K can be expressed as the change in A concentration over the change in time, and we measure concentration as molarity, as moles per liter, and our standard unit of time is the second. So moles per liter per second would be an expression, the units of this small k reaction constant. Now, higher order reactions will depend on concentrations of different reactants, particularly. There can be intermediate states which would be considered products or reactants. It gets very much more complicated than the scope of first-year accelerated chemistry to worry about higher order reactions. Beyond a first order reaction, we're good for now. Now, we do determine all of these reaction rates from experimentation. In this particular case, you can see that if I increase my concentration of hydrogen iodide, I double my rate of reaction. If I double my concentration of hydrogen peroxide, I also double the rate of the reaction. So what this tells me is that I have two different components. Each of them are dependent on, I'm sorry, I just got a text that completely distracted me. Each of these are dependent on, so for the reaction rate to proceed, it's dependent on the concentration of hydrogen iodide. It's also dependent on the concentration of hydrogen peroxide. This would be a higher order reaction, not a first order, because there's two components. There might also be some intermediates in here, which would possibly need to be considered, but that would be when you get your PhD in physical chemistry. We don't need to worry about that at the moment. Just to understand, if I'm increasing concentrations, I can increase rate. That is what you would need to know from looking at a table such as this. And we know the concentrations of both are affecting the reaction rate. Now, again, I may ask on a test, how could I change a reaction rate? If I raise the temperature, and I actually took out my slides now that I'm seeing about collisions, because that was on my, okay. I'll need to refer back to those slides. If you remember that reactants must collide and form a reaction complex, an activated complex, in order to react. If I raise my temperature, I'm increasing the number of collisions between particles, which would actually increase my reaction rate. So I will make sure this will be the second part of my presentation, because I have my slide with the activated complex on the other set of slides. So this will be part two. Concentration If I increase the concentration of any reactant, I'm going to increase my reaction rate, because even if I increase the concentration of just one reactant, I'm still increasing the collisions between my reactant molecules. One increase in concentration still would increase the number of hits with the other reactant. Particle size, we are decreasing the surface area relative to mass, which is going to mean that you can have more hits on the surface per unit of mass, and therefore the reaction will increase. What catalysts do, and I'll have to refer back to my graphs with the activation energy required for a reaction to occur, catalysts will lower the activation energy and therefore make it easier for the reaction to proceed. So temperature will speed up a reaction rate, and concentration will speed up a reaction. Increasing concentration will speed up a reaction rate. Decreasing particle size will increase your reaction rate, and introducing a catalyst will also increase our reaction rate. Referring back to what we talked about with heat and entropy, these are all interplays between heat and entropy. And reactions will reach a state of equilibrium when the concentrations of reactants and products stay constant at a specific temperature and pressure. As we will see, reaction equilibrium constants that tell us the progress of a reaction, or where a reaction would be more likely to end up with more product or more reactant, they're very much dependent on different temperatures and different pressures. Reaction rates, both forward and backward, determine the status of reactants and products at an equilibrium. Now, this one, we've seen it before. I'm introducing dinitrogen tetroxide, and I'm also producing nitrogen dioxide. This is a reversible reaction. It might actually be better if I wrote the dinitrogen tetroxide on the left side, just to see, because that was what originally came into this container first. But what actually happens is this has a certain speed rate of reaction. This has a certain rate of reaction. When these two come into balance, then we reach equilibrium. Now, you'll see a lot of generalized problems. If you go on to AP, you're going to see a lot of generalized problems with A referring to one element or compound, B referring to another element or a compound, and then C and D are your products. The small letters are your coefficients. So if I had 1 nitrogen plus 3 hydrogen would give me 2 ammonia. That would be an example. And that actually would be an even better example, because I'm doing a combination reaction here. I could also have a decomposition reaction where something falls apart and becomes 2 things. So maybe this would be 2 hydrogen peroxide would be 2 water, and 1 oxygen molecule is another example. And when we reach an equilibrium at a certain temperature and pressure, if I started with sulfur dioxide and oxygen, and let's say I had, 2 moles of sulfur dioxide to 1 mole of oxygen, I would end up producing eventually a certain amount. I would make, about 1.5 moles of sulfur trioxide at a certain temperature. So if I started with sulfur dioxide and oxygen, I would make a certain amount of sulfur trioxide. If I only started with sulfur trioxide, and eventually I would actually reach an equilibrium where we still have the same amount of sulfur dioxide and the same amount of oxygen. The meaning of equilibrium at this particular temperature and pressure is whether I start with these 2 reactants, I make that product, they all come into balance, or I start with this reactant and these 2 products, it will decompose to form the same balance. This is the equilibrium. This is the state where everyone is happiest at that particular temperature and pressure. I thought this was kind of a cool graph, although we have time running in different directions on both sides of the graph. Now here's where I need to improve my animation a little bit, but my generalized equation is my little a, and then so my coefficient and my reactant concentration, my reactant, and then it will become concentration down here. My coefficient and my other compound. And what I end up making is this equation. I'm just basically plugging in numbers. This means concentration, moles per liter of a certain compound. These would be my products, these would be my reactants, and then they are all raised to a coefficient. Now, I had attempted to explain why this happens. It was just a convenience to think of it that way. It certainly isn't the actual meaning behind the law of mass action, which again would require very advanced knowledge of certain concepts in physical chemistry, which we don't really need to get into at this point. What I wanted you to understand is you can still plug numbers into this equation without understanding all of the reasoning behind it. Newton's laws of gravity work very well. You can plug numbers into Newton's laws of gravity, even though we don't understand gravity very well or really at all. Still, Newton's laws with those equations do work perfectly fine. Now, what you need to know about KEQ, my equilibrium constant, if it's far greater than 1, that would be my top. My concentration of products would be far higher than my concentration of reactants, which would mean I get a very big number, far larger than 1. If my concentration of reactants is way higher than my concentration of products, KEQ is going to be a very small number because I'm going to have a huge number down here and a small number up top. Homogeneous equilibrium will apply to reactions where the reactant species are in the same phase. This primarily will be with reference to gases, all of my reactants and products being gases, or solutions. I might have different aqueous compounds, which are reactants and products. That's very important when we talk about solubility product constant, which will be coming up fairly soon. Just to kind of reiterate, I found these slides. I thought this might be helpful. So if my concentration of hydrogen bromide is way higher than my concentration of hydrogen and bromine, I'm taking that concentration, I'm squaring it. I'm going to get a pretty darn big number here, which is what my KEQ would be equivalent to. In this particular case, I have nitrogens, I have oxygens. I have a lot of nitrogens, I have a lot of oxygens. I have very few nitrogen monoxides. So what would happen? I have a small number at the top. I'm squaring a small number, making it even smaller, possibly if it's something less than 1. And then I have my concentrations down here, much larger. Small number divided by a big number is going to be a really small number. Just get used to that, become familiar with that. So, now we need to know how to read a word problem at a specific reaction temperature. If it gives you a reaction temperature, doesn't matter. It's just thrown in there to confuse you at this time. What you need to worry about is the temperature is not part of your calculation because equilibrium constants change with temperature, they change with pressure. What you need to worry about is that carbon monoxide and water vapor, so these are two gases, react to form hydrogen and carbon monoxide in a system that comes to equilibrium with the following concentrations. So I need a balanced reaction. Notice 1 carbon, 1 carbon, 2 oxygens, 2 oxygens, 2 hydrogens, 2 hydrogens. This is a balanced equation. I have coefficients of 1, so that's a fairly friendly problem. I have my equilibrium constant equation. Again, you can write this on a card, but you need to remember products are C and D, reactants are A and B. What you need to do now is plug in the concentrations that you were given. So concentration of carbon monoxide would be down here. Concentration of water would be down here. Concentration of hydrogen and concentration of carbon dioxide. Would I expect to see a big number here? Well, let me see. My concentration of hydrogen and my concentration of carbon dioxide are both fairly large. This is extremely small, so yeah, I should expect to find a number probably greater than 1. Everything in these concentrations is raised to the power of 1, making my math a lot easier. I reversed the animation there, but I end up getting a number 134, which means my products, because they occur in higher concentrations, my products are favored in this reaction. Reactants, this one has a fairly high concentration, but that one has a ridiculously low concentration. Here's another one. At a specific temperature, sulfur dioxide and oxygen gas react to form sulfur trioxide. KEQ is 85.0, which again means products are being favored. What would the concentration of sulfur trioxide be if the concentrations of both sulfur dioxide and oxygen are 0.0500 molar? I have two concentrations. I have an equilibrium constant. I'm not going to solve for equilibrium constant because I already have it. I'm not going to solve for the concentrations of sulfur dioxide and oxygen. What I will be solving is the concentration of sulfur trioxide. So to start this off, I need a balanced equation. I said sulfur dioxide and oxygen gas react to form sulfur trioxide. Then you would have to balance it. So two sulfurs, 6 oxygens and 6 oxygens. I'm all balanced. Okay. Now, that is my equilibrium constant again. Now, here I know 85 is the number here. Sulfur dioxide and oxygen are reactants, so they're going to go on the bottom. How many products do I have? I only have one. So I need to put that concentration of sulfur trioxide, and I need to square it because it has a 2 in the coefficient, which means that if you wanted to set this equal to X, equally valid way of looking at this, but it's concentration of sulfur trioxide. I had to square the sulfur dioxide concentration because my coefficient is 2, and I have this raised to the power of 1 because there is no coefficient for oxygen. What I end up doing, I do my math down here. I square this, I multiply it by that. I end up getting a number, which you would then multiply by 85.0. I think we can do algebra. I don't have ability to put all that stuff onto a PowerPoint. I could write them out, but I think we're okay with that sort of stuff. I would end up getting sulfur trioxide concentration squared, which then I just need to take the square root, and I would get 0.103 molar. Now, does my answer make sense? You're going to have to learn to make sense of these answers. 85.0 is my equilibrium constant. That means products would be favored, which means concentration of sulfur trioxide should be higher than my concentrations of sulfur dioxide and oxygen. Sorry, I had to yawn there for a moment. Anyway, that is concentration. These are my reactant concentrations. That is my product concentration. As it turns out, my product has a higher concentration than my reactants. Does that make sense with this equilibrium constant? It absolutely does. Okay. Now, another way of looking at equilibrium or determining if a system is at equilibrium is to use something called a reaction quotient. Now, reaction quotient can be used with any concentration of products and reactants. This is valid at an equilibrium only. So what happens in this case? If I have a Q value with any concentration of these numbers, I can compare that to my equilibrium constant and see, is my reaction at equilibrium? If my Q value equals my KEQ value, then the system is at equilibrium. If I have a greater KEQ, that means that my numbers up top, if I have a greater KEQ compared to Q, that's going to mean that my numbers up top are going to have to increase, which means I need to form more product in order to get to equilibrium. If my KEQ is less than Q, that means I'm going to have to lessen my product on top and increase my reactants to lower the number down to KEQ, which means then that reaction will proceed towards the left. I will increase the concentration of reactants relative to products. Again, I could explain it over and over, but really it helps by doing some problems. So I would calculate Q based on concentrations that I am given. I'm given a KEQ value. So I need to compare this KEQ value to my reaction quotient value by plugging in these particular numbers. And for that, I need a balanced equation. So Q, this C refers to concentration. KC is concentration. It's the same as KEQ. We're going to see KA. We're going to see KB. We're going to see KSP. It's all equilibrium constant calculations. You do not need to worry about what each of these letters mean. It's all KEQ, and it's all Q as a reaction quotient. So I'm calculating my reaction quotient based on my concentrations. This is my product. These are my reactants. I have to raise these to the power of their coefficients, and then I end up getting 6 squared, which is 36, over 16 times 2, which is 32, which gives me a number of 1.125. That tells me that my concentration of fluorine dichlorine oxide needs to, actually that's what you could call it, but there's other names for it anyway. This tells me that particular compound needs to increase in concentration in order to get to my equilibrium constant of 5.10. So this number Q being less than the equilibrium constant means that the reaction is not at equilibrium, and we will need to make more product and reduce the amount of reactants in order for this reaction to reach equilibrium. Le Chatelier's principle, I've mentioned, I've touched on it, I've said some things about it. What you need to understand is that a system at equilibrium will respond to a stress or respond to a change by changing equilibrium concentrations. This is what Haber figured out with the nitrogen and hydrogen and ammonia reaction. This is another example. So it takes sulfur dioxide and oxygen. I make sulfur trioxide. I also produce heat. So with our equilibrium concentrations, heat is not a factor. However, when I'm working with a Le Chatelier's principle problem, which is basically just to describe what's happening in this particular case, it's a concept more than a calculation, I will actually be able to consider the incorporation of heat. Heat is treated as a product. Sulfur dioxide, oxygen are my reactants, and sulfur trioxide is another product. It should be fairly self-explanatory. If I remove my sulfur trioxide, well, then more sulfur dioxide and oxygen are going to react to form more sulfur trioxide. If I remove heat, the same exact thing happens. This is a product. If I lower the temperature of my equilibrium mixture, I'm going to end up pushing this to the right. I'm going to make more sulfur trioxide if I lower the temperature, removing a product, which is heat. If I decrease the pressure, that allows space for more gas molecules. Here I have 3 gas molecules. Here I only have 2. If I increase the pressure, these 3 gas molecules would be compressed into 2 gas molecules. If I removed oxygen, well, that would be like the reverse reaction. More sulfur trioxide will decompose to replace the oxygen that is taken out. So I'm going to shift my reaction to the left. If I add sulfur trioxide, same thing. I'm going to increase the amount of sulfur dioxide and oxygen that would form from decomposing sulfur trioxide. If we change pressure, this is what Haber figured out. So you take nitrogen and you take hydrogen, you compress them, you end up making more ammonia. So Le Chatelier and Haber figured out that if you compress gases, they will react to relieve the stress of all of that added pressure by going from 4 moles to gas to 2 moles. You've cut the pressure in half. The pressure that you increase, you've cut it in half by taking 4 moles of gas and reducing it to 2 moles of gas. This does not have any influence on reactants in aqueous solution because no amount of pressure is going to bring those molecules closer to each other. As I've said, this is an extremely important system. If we as a species are adding CO2 to the atmosphere, that means more CO2 goes into the ocean and becomes carbonic acid, which means more hydrogen ions pop off of the carbonic acid, form hydrogen carbonate, which is much less accessible to aquatic organisms that build calcium carbonate skeletons, and therefore the acidification of the oceans has a tremendously detrimental effect on ocean life. We saw the Haber process. This is another outlining of the Haber process. I probably don't need this slide with the others necessarily, but same idea. I'm taking hydrogen and nitrogen, I'm squeezing it down, I end up making more ammonia because the system is changing to reduce the stress on the system. So what Haber figured out, and again, this is all within the context of Le Chatelier's principle, high concentrations of nitrogen and hydrogen are going to push the reaction to the right. Removing the ammonia is also going to push the reaction to the right. If you lower the temperature, if you remove the heat, you're also going to push this process to the right. If you add a catalyst, if you blow nitrogen and hydrogen over platinum, which has a specific size that allows the atoms of platinum have a specific arrangement that allows nitrogen and hydrogen to come very close together for this reaction to proceed, that's also going to drive the reaction to the right. And high pressure also, you're keeping that ammonia from decomposing because it's going to try to maintain the smallest number of moles of a gas, and that's why you would also be able to maintain higher levels of ammonia. So I hope all of that makes sense. I will post this as quickly as possible, and I'll get the other videos as well.